Okay, welcome to lecture 17 of Unit 2, Higher Order ODEs. And so today we're moving on to how we solve a different type of linear nth order ODE. Okay, and this is going to be called the Cauchy-Euler equations. So previously we have learned how to solve nth order linear ODEs, homogeneous ODEs, with constant coefficients. Okay, these Cauchy-Euler equations are going to be equations with non-constant coefficients. Okay, but they're very special non-constant coefficients. Okay, as we'll see now. So the nth order linear ODE, a of n times x to the power of n times the nth derivative of y with respect to x plus the next term would be a n minus 1 times x to the power of n times the n minus first derivative of y with respect to xn, all the way down to some constant a1 times x times dy by dx plus some constant a0 times y equals some non-homogeneous term. So all the AI's here are constants. Okay, but we have these terms x to some power in front of these derivatives. Okay, this is called the Cauchy-Euler equations. Okay, so this would be a Cauchy-Euler equation of nth order because the highest derivative is order n. Okay, so this differs from the nth order ODEs with constant coefficients by the presence of the xn term. So we've got an xn here and x here. Okay. And the key point is that the power of the x, so x to the power of some number, is always the power of the order of the derivative. So x to the power of n for the nth derivative, x to the power of 1 for the first derivative, and you could say x to the power of 0 for y itself, or the 0th derivative. Okay. So again, this is called the nth order Cauchy-Euler equation, but in this class we're just going to focus on the second order version, and in fact the second order homogeneous version. So in this class, the Cauchy-Euler equation we will be focusing on is some constant a times x squared times the second derivative of y with respect to x plus b times x times dy by dx plus c times y equals 0. So a, b, c are constants. We have an x to the power of 2 for the second derivative and x to the power of 1 for the first derivative. Okay, so our second order homogeneous Cauchy-Euler equation here, again note that the highest order coefficient, so ax squared y double prime, this is equal to 0 when x equals 0. So we have problems with existence and uniqueness when x equals 0 here. So for the second order homogeneous Cauchy-Euler equation, we're going to focus on solutions that are on the interval 0 to infinity, not including the endpoints here. Okay, so that avoids any issues with existence and uniqueness. Therefore, on this interval 0 to infinity, we're guaranteed to have a unique solution. So how do we find solutions to this ODE? Well, recall for second order linear ODEs with constant coefficients, we had solutions of the form y equals e to the mx. So some number m1 here, y equals e to the mx. For the second order linear homogeneous Cauchy-Euler equations, which has non-constant coefficients, right? We've got an ax squared here and a bx here. We're going to look for solutions of the form y equals x to the power of m. Okay. So if we are looking for solutions of this form, this polynomial, let's take the two derivatives of this function y and use it in the differential equation to understand what our solutions are going to look like. Okay, we'll take our two derivatives, so we get well, the derivatives of a polynomial are quite straightforward. The first derivative is going to be m times x to the m minus 1. The second derivative is going to be m times m minus 1 times x to the power of m minus 2. Okay. But it turns out that the second derivative here, we're going to have an x to the m minus 2, but we're going to be multiplying that by x squared, so we're going to end up with an x to the m in the second derivative here. The first derivative, we're going to have m times x to the m minus 1, but we're going to be multiplying that by an x, so we're going to get an x to the m here. And similarly, the y term here, we're going to get an x to the m as well. So it turns out that taking this solution y equals x to the m, taking its two derivatives and substituting it into the ODE, we get this constant term x to the m. And this is never equal to 0 on our interval, which is the positive real line, right? 0 to infinity, not including 0. So we can divide this common factor out throughout the whole equation, and we end up with simply I take out the common factor here, I can divide through by x to the m now, and I end up with a times m squared plus b minus a times m plus c equals 0. So this is just this term in the bracket here, just slightly rearranged. Okay, slightly rearranged, so we have the m squared, the m terms by themselves, and the constant term. So this equation here, the a, the b, and the c just come from the original differential equation, the original Cauchy-Euler differential equation. And this is called the auxiliary equation for the second order homogeneous Cauchy-Euler equation. Okay, so therefore y equals x to the m is a solution to the second order Cauchy-Euler equations whenever m is a solution to this auxiliary equation. But again, this is just a quadratic, right? So we can solve this for m. We can find our two solutions for m very easily. So there are again going to be three possible cases, right? Three possible cases are distinct real roots, so where we have m1 is not equal to m2, and both m1 and m2 are real. In that case, our general solution is simply going to be c1, so some constant c1 times x to the m1 plus c2 times x to the m2. Case 2 is we have repeated real roots, so m1 equals m2. So we only have one root to that quadratic. Okay, and if that's the case, our general solution to the ODE is y equals c1 times x to the m1 plus c2 x to the m1 times log of x. Okay, now this second solution here, this falls out of using the method of reduction of order. So if you recall, for the constant coefficient case, we had one solution which was c1 e to the mx, and we had to find a second solution using the method of reduction of order. It turns out if you apply that method of reduction of order to the first solution here, x to the m1, then we get the second linearly independent solution, x to the m1 times the log of x. You're welcome to try this yourself, and it's actually not a very hard proof. The proof is also in the textbook if you'd like to look there. But just for time, I'm just introducing these three cases here. And of course, the third type of solution we can get from this auxiliary equation, this quadratic, is complex conjugate roots. So m1 equals alpha plus I times beta, m2 equals alpha minus I beta, and our solutions, where alpha was the real part of the root and beta was the imaginary part of the root. And our solutions look like the form y equals x to the power of a. So this is quite similar to what we had before. We had, for the constant coefficient case, we had e to the power of alpha x. Here we just have x to the power of alpha times c1 cosine beta log x plus c2 sine beta log x. Okay, so these three cases here and these are the three general solutions for the three possible cases, which are determined by the roots of this auxiliary equation. Note that the third case here, complex conjugate roots, the solution for this case just falls out of a little bit of algebra. So if we have x to the power of the imaginary number I times beta, we can rewrite that, if we like, as the exponential of the log of x all to the power of I beta. Okay, because again we're dealing with x is positive. If we take the log the exponential of a log, we just get x back, and then I can raise that to the power I times beta. So these are equivalent statements here, but I can use the properties of the exponential function to rewrite this right-hand side like so. I can bring the power inside the exponential. Okay, and then this looks like the Euler identity, right? We have the exponential of some I times something else. So I can use Euler's identity on this exponential here, and we get the solution shown above here. Okay. But really, for this Cauchy-Euler equation case, I really just want you to focus on this slide here. If we have the second order homogeneous Cauchy-Euler equation, we have the auxiliary equation am squared plus b minus am plus c equals 0. And we get three cases depending on the roots of this quadratic equation. And the three cases, distinct real roots, we get the general solution of this form. Repeated roots, we get a general solution of this form here. And complex conjugate roots, we get a general solution of this form here. So again, this is almost a case of print this out and stick it on your wall so that you can remember the solutions to the Cauchy-Euler equations. So let's look at some examples. Okay, example 1, 2x squared y double prime plus 3x y prime minus 15y equals 0. So again, this is obviously a Cauchy-Euler equation because we have an x squared times the second derivative of y. We have an x times the first derivative of y, and we have just a constant times y here equals 0. We can identify a equals 2 here, b equals 3, c equals negative 15. I can look at my auxiliary equation and use those numbers in the auxiliary equation. 2 times m squared plus b minus a, 3 minus 2m, minus 15c, plus negative 15 equals 0. And, well, feel free to go away and use your quadratic formula to find that the two distinct roots for this equation are m1 equals negative 3 and m2 equals 5 halves. Okay, let's go back to our cheat sheet here and say, okay, well, in the case of distinct real roots, our general solution is just c1 times x to the first root plus c2 times x to the power of the second root. So therefore, I can write my general solution for this second order Cauchy-Euler ODE as c1 x to the power of negative 3, so negative 3, this first root here, plus c2 x to the power of 5 halves. So 5 halves being this second root here. Okay, so again, if you remember this cheat sheet, or if you have it printed out sitting next to you, then solving these Cauchy-Euler equations, the homogeneous Cauchy-Euler equations of second order, is quite straightforward. Let's look at some other examples. Again, you can see that we have a second order homogeneous Cauchy-Euler equation here. We can identify these coefficients a equals 1, b equals negative 7, and c equals positive 16. I can write down my auxiliary equation and substitute a, b, and c into this equation. So a is 1, so I get m squared. B minus a is negative 7 minus 1, which is negative 8, plus c is 16, equals 0. What we should find here is that we have a repeated root, m1 equals m2 equals 4. And again, if I refer back to my cheat sheet, then in the case 2 of repeated roots, my general solution is c1 times x to the power of the root plus c2 times x to the power of the root times the log of x. So quite simply, the general solution to this Cauchy-Euler equation is c1 x to the power of 4, where 4 is the root of this quadratic, this auxiliary equation, plus c2 times x to the power of 4 log of x. So again, c1 and c2 are some unknown constants here, which we could solve if we had an initial value problem. Okay, and finally, let's look at an example where we're going to have complex conjugate roots. So again, we've got a second order homogeneous Cauchy-Euler equation here. Our coefficients a is equal to 1, b is equal to 3, and c is equal to 4. My auxiliary equation here, I can use these numbers in there. A is 1, b minus a is 3 minus 1 is 2, c is 4, so we end up finding that the first root of this quadratic or this auxiliary equation is negative 1 plus square root of 3 times the imaginary number and its conjugate. Again, referring back to the cheat sheet here, the solution, the general solution in the case of complex conjugate roots is x to the power of alpha times some constant c1 cosine beta log of x plus c2 sine beta log of x. Okay, where alpha and beta are the real part of the root, so negative 1, and the imaginary part of the root, so square root of 3. Therefore, I can write my general solution to the second order homogeneous Cauchy-Euler equation as x to the power of alpha, where alpha is negative 1, which is the real part of the root, times c1 cosine beta, the imaginary part of the root, so square root 3, log of x, plus c2 sine beta times log of x. So again, if you keep this slide handy, maybe even if you print the slide out, you will be able to solve these Cauchy-Euler equations, the second order homogeneous Cauchy-Euler equations, in a fairly straightforward fashion. Okay, so this lecture is actually going to be a combination of lecture, I think this is lecture 17 and lecture 18. So we're going to move on to a new set of slides now. Okay, so we're sort of having two half lectures today. In what I'm calling lecture 17, we just learned to solve the Cauchy-Euler equation, or at least the second order homogeneous version of that. And in the second half of this lecture, which I'm calling lecture 18, we're going to look at solving simple systems of linear ODEs, okay, using a method called systematic elimination. Now, we are going to learn a general way to solve systems of linear ODEs in a future unit. I believe it is unit 4. But this is just an introductory method which we can use to solve very simple systems of linear ODEs. So consider we have a system of two ODEs here. So there is only one independent variable, that is t, so that's the thing we are taking the derivatives with respect to. There are two dependent variables here, so x and y are both dependent variables. And so these two differential equations, they are both, in fact, they're both linear. These form a system of differential equations. So often when we're modeling something in the real world, it will take more than one differential equation to model that system. So for example, if you take the solar system, the sun is in the middle of the solar system, and there are multiple planetary bodies, moons, asteroids, and whatever else is out there, orbiting the sun. The motion of each of them is governed by a differential equation. It's basically Newton's one of Newton's laws. But you will end up with a differential equation for each planetary body orbiting the sun. Okay, so we end up with quite a large system of differential equations. So often we are having to solve multiple differential equations at the exact same time. Or another example is if we had some kind of chemical mixture. Let's say we were trying to produce steel and we were melting down a bunch of different elements. We potentially have differential equations for multiple chemical reactions, for multiple species in a chemical reaction. So differential equations quite often come in a set. So in the particular system we're looking at here, it's in a set of two. So we have two differential equations. Again, x and y are dependent. T is the independent variable. I can rearrange these equations to write them so that the right-hand side equals 0. So I can write these as dx by dt minus 3y equals 0, dy by dt minus 2x equals 0. And the reason I want to do that is because I want to actually write these these ODEs using differential operators. Okay, so if you recall, in a much earlier class, we talked about differential operators, and basically what we said is that we can write derivatives dx by dt, for example, as just big D times x. We can write the derivative of dy by dt as big D times y. So I can write my system using this differential operator notation, which I've called equation 1 and 2 and have rewritten up the top here. Okay, well, what I'm going to do is I'm going to try to do a trick from algebra when we have a system of equations, and I'm going to use this thing called systematic elimination. So I'm going to multiply this first equation by the differential operator d, and so if I do that, I get d squared times x minus 3 dy equals 0, and so that's represented by equation 3 here. And I'm going to multiply the second equation here by the constant number 3. And so if I do that, then I get negative 2 times 3 times x, so negative 6x, plus 3 times d times y, plus 3 times d times y, in equation 4 here. The reason I want to do this is because now you can see if I add these equations 3 and 4 together, this 3 times d times y term is going to cancel out. So I end up with d squared x minus 3dy minus 6x plus 3dy. So these 3dy and negative 3dy dy cancel out, and we get left with a second order linear ODE with constant coefficients. So d squared x minus 6x equals 0. Of course, I know exactly how to solve this equation. This is, again, like I say, a linear ODE, homogeneous linear ODE with constant coefficients. I can write down the auxiliary equation for this case, m squared minus 6 equals 0, which has two distinct real roots. m1 equals square root 6, m2 equals negative square root 6. I'm missing the equals here, sorry. And therefore I can write down the general solution for x here, x of t is equal to c1 times e to the negative square root 6 t, for some reason I've used this one first, plus c2 times e to the square root 6t. Okay, so again, these linear ODEs with constant coefficients, they come up very, very frequently. So please make sure you know how to solve them. So now I have a solution for x of t, but I had two equations, right? So I need a solution for y of t as well. Well, that's not too bad. I can come up with a solution for y of t. Here I basically eliminated dy. Well, now I can do the same thing and eliminate dx. So if we start again, I can multiply equation 1 by the constant 2. So I end up with 2dx minus 6y equals 0, represented by equation 3 here. And I can multiply equation 2 by the differential operator d. So I get d squared y minus 2dx equals 0, represented by equation 4 here. Again, I can add equation 3 and 4 together to get d squared y minus 6y equals 0. So the 2dx here, I get a 2dx minus a 2dx here. They cancel out. Again, it's an ODE with constant coefficients. It turns out actually to have the same roots as the previous equation, and therefore we can solve this ODE. Y of t equals c3e to the minus square root 6t plus c4e to the square root 6t. So we can represent our two solutions here like so. Okay, but there is a little bit of a problem here because we had a system of two equations, two first order equations. So in order for it to be a general solution to the system, we should only have two constants, two unknowns here. Whereas now we have four. We have C1, C2, C3, and C4. So there was an issue here that we have four unknowns, but only two first order equations. So we've got too many unknowns. We need to write actually two of the unknowns in terms of the other two unknowns. So we're going to try to express the constants C3 and C4 in terms of the other two constants C1 and C2. So let's use these ODEs, x equals this thing, y equals this thing, in the original ODE system. So remember that original ODE system was dx by dt equals 3y, dy by dt equals 2x, and of course I can differentiate these equations, these solutions with respect to t. So let's focus on dx by dt equals 3y. dx by dt is just the derivative of the solution of x here. So we're going to get it's the derivative with respect to t of this solution x of t here. And if I do that, basically we're differentiating an exponential, so I'm going to get a negative square root 6 times c1 times e to the negative square root 6t plus square root 6 times c2 e to the square root 6t. Okay, so that's the left-hand side of this equation here. The right-hand side is 3y, so we should calculate 3y as well. 3y is just 3 times c3e to the negative square root 6t times 3 times c4e to the square root 6t. And so my left-hand side should equal my right-hand side, so my dx by dt here should equal my 3y. And so, well, now we have one equation where we should be able to relate c1 and c2 to c3 and c4. Okay. So let's rearrange that equation. Pulling out the common factors of the exponentials. So here I have the exponentials of negative square root 6t. Here I have the exponential negative square root 6t. So there's a common factor in these two terms. And similarly, there is a common factor of the exponential of square root 6t in the other two terms. So I can rearrange that equation and write it like so. Okay, and since the exponential function is never 0, okay, I know that these two terms individually must be equal to 0. Okay, so let's set the two bracketed terms equal to 0, and therefore we are given, or what falls out of these two equations, a relationship between C1 and C3 and a relationship between C2 and C4. So therefore, the solution to the linear system of ODEs is given as so, where we've replaced C3 and C4 by these relations between C3 and C1 and C4 and C2 here. So systematic elimination is a way of solving very simple systems of linear ODEs. Again, in Unit 4 we're going to learn some new techniques to solve different types of systems of ODEs. Okay, and so that's going to be using a lot of our linear algebra methods such as eigenvalues and eigenvectors. So we can look forward to that. Okay, thank you very much. We're almost through all the material for Unit 2 now, but in the remaining maybe 2 lectures, we're going to cover an application of second order linear ODEs. And so this is basically going to be a spring mass system. So I look forward to seeing you in the next lecture, and we will talk about applications of these higher order ODEs. Thank you.